All right, good day, mates. We are going to start talking about the definite integral today. As you can see over here in the title of this section, we're hopping around chapter 4 because I like to do it how I like to do it. So we're going to go to 4.3 and then we'll come backwards to 4.2 later. So 4.1, just a reminder that what phrase we did not use when we learned about integrals that first day is the indefinite integral. Okay, so the indefinite integral looks like this. If I give you a function, the answer to that indefinite integral is the antiderivative plus the constant of integration. Right, so today we're introducing an idea called a definite integral. So a definite integral looks similar, but a little bit different. You'll notice it has values a and b, which are limits on the function that is the integrand. Okay, so if you look down at example 1, those limits are -2 and 2, and we'll talk about what that signifies. And what this is that this calculates the net area under the curve. So we're going to talk a lot about area today, okay, and what we mean by net area. So the indefinite integral is indefinite because of that mysterious constant of integration. There's nothing definite about that function that solves that problem. But the definite integral, the answer is a number. We're going to make a calculation about area. So that's the difference, the big idea difference between section 4.1 and today's lesson. So moving on to example 1, let's kind of see if we can make sense of this. So what we've got here is we've got some limits on a function. So again, this integrand means we're talking about the function y equals square root of 4 minus x squared. And then these are x values here that limit what portion of the x-axis we are talking about. So what we're going to try to do to come up with this answer is we are going to try to sketch it. So here's like -2 and 2 on the x-axis. You can sketch beyond that, but I mean, if you know what this function looks like, it doesn't really go beyond that. Let's put it in pink. So up here at +2, this is the semicircle, right? I know it doesn't look like a semicircle, but let's just imagine with our brains that I'm good at drawing a semicircle. Okay, and so what we're talking about is all this space right here. When you take physics class, right, you talk a lot about the area under the curve when you make your calculations, probably for position. So it's kind of a similar idea tied directly to that. In fact, we're going to study the physics component later on. So in order to come up with the answer to this question, we have to calculate the area of this space. And again, we're going to talk about the net area. So we know this is a semicircle and that the area of a semicircle is 1/2 pi r squared. We know that the radius of this circle is 2. So simplifying that, 4 divided by 2 gives me 2 pi. And so my answer to this problem is 2 pi. It's representing that pink space. Okay, so nothing too tricky going on. Hardest part of that is probably knowing what the square root of 4 minus x squared looks like. Okay, let's go on to another one here. Again, the tricky part right now is that we don't have any grid lines. We don't have any, like formal boxes to count or anything like that. So we're just doing these kind of rough sketches of these functions and seeing what they look like. So for example 2, let's talk about graphing. Again, y equals 1.5x plus 5. You can think of it that way. So let's see. My y-intercept for 5 is up here, and my slope is down 3/2 is +1.5. So let's say this function looks like this. And then again, we are counting from 0 to 6. So here's 0 on the x-axis, and then 1, 2, 3, 4, 5, 6. 6. Here is the space we're talking about. So we kind of have to know what that goes up to on the function. So if I plug in 6 to the function at that moment, I get, 14, I think. Let's double check that. 9 plus 5, yeah. So we're talking about between 0 and 6, and we're talking about that space under the x. Well, I should really say between the x-axis and the function itself. So this time we get a new shape. So I want you to think about what shape this is, right? You could split it up into, you know, a square and a triangle, but we're going to try to do it like as an actual trapezoid because that'll help us with our work later. So think about the area of a trapezoid. What is that area formula? Okay, should be height over 2, and then we sum the bases, so hopefully that rings a bell from the last time you calculated area. So the strange part about this function, right, when we talk about area, we're actually talking about this distance here between the parallel bases, right? So the area of this trapezoid is 6 units divided by 2, and then the length of the bases are calculated with these yellow, right? The first base is 5 units long. Well, geez, you can't see that. 5 units long, plus the second base, right, we calculated is 14 units long when we plug in 6 to the original function. Okay, so this would be our answer. 3 times 19, I guess. Is that what that says? 319. So 57 would be our answer for this one. Okay, now we, to this point, have not addressed what this idea of net area means. So that's going to pop up here in example 3. So let's do the same thing. Let's try to graph y equals 2x. I'm going to generate a little grid here. So it has a y-intercept of 0. You know, try to space these out evenly as you can on your paper. It's not paper. On your screen. And sketch y equals 2x. Okay, and then again, we have to kind of cordon off what x values we're talking about. So we're talking about -2 to +1. Okay, so when we, again, like I said before, talk about the space between the function and the x-axis, we are talking on this side, if I drop down like a vertical line, we're talking about this pink area here. And then on the other side of the triangle, we're talking about this tiny orange triangle here. So we have these two triangles that we're trying to add up together. Oh my God, why can't this sketch? Okay, so we're talking about these two triangles here. So this is where the idea of net change comes to be. So I want you to take a minute. Again, I think this passes through, technically this is -4, right, in length here. And when we plug in 1 to the function, this does come up to 2. So that part of the drawing looks good. So I want you to calculate this area of the pink triangle and the orange triangle. So the pink triangle's area should be 1/2, its base is 2, and its height is 4. We don't want to report area as negative, so 8 divided by 2. The pink triangle is 4 units. And then the orange triangle, I'll do this in a different color here, should be 1/2. Its base is only 1 unit, and its height is 2. So that has an area of 1. So what we're going to do when we write down the answer to the original question, the integral of from -2 to 1 of 2x dx, our actual answer to this integral is -3. So I want you to think about why we would put -3 as an answer, okay, and then stick that in the question. And the reason that it is because the pink triangle counts as a negative integral. So we don't ever want to talk about the area of that pink triangle as being negative. Because it's situated below the x-axis, it counts as negative integral, okay? So if we look right here, I'm going to kind of put this note down. The pink triangle's area is positive, but the value of its integral is negative. So when we compile that information together to get -3, right, we're technically doing -4 plus 1. Okay, so kind of a fun thing. So this is the idea of this net area under the curve, meaning if we take what's above the x-axis as positive integration and what's below the x-axis as negative integration, the net of all that area is what we report as our answer. So that's why it's a -3. All right, so a couple properties here, cut and pasted right from the book. The first one is really fun. It says if f is defined at x equals a, then we define the integral from a to a of f of x is equal to 0. So when those two limits match, like integrating from 2 to 2 or 5 to 5, our overall value, of course, is 0 because we're not calculating any area. The next one has us switching these limits. So if we have an integral and we flip-flop where the a and the b are, what happens is that the values of those two integrals are opposite. So if I say the integral from 2 to 3 is 5, then the integral from 3 to 2 would be -5. So we'll do an example like that down below here. And then the other properties in the second box, just kind of talk about how we address these constants. So if you have a constant times a function, you can just multiply the overall integral of the regular function times that constant. It's the same thing. And then number 2 says that you can separate out these integrals and do them one at a time, and you can you can apply the limits to each, f and g, and then add them in the end. And that's the same as having a single integrand of f of x plus or minus g of x. So an example 4 here, we're going to make use of these. We're given some information here, so it's important to note this is not a multiple choice question. So, this is saying that we have the integral from 0 to 3 of a function is 4. We don't know what the function is, we just know the value of its net area is 4. And then here, from 3 to 6, we get -1. Okay, so now we're supposed to do these 4 different calculations, and they're making use of some of these theorems above. So the first one is saying, well, what's the integral from 0 to 6? Well, that would be, right, combining 0 to 3 plus 3 to 6, right? 4 plus -1 gives me 3. So that's part A. Part B is flip-flopping those integrals, limits, right? So this is the same as the opposite of 3 to 6, and since 3 to 6 as given to us is -1, then the flip-flop of that is going to be +1. Part C has those matchy limits here. If we integrate from 3 to 3, right, that gives us 0. And then part D, if we integrate from 3 to 6, we're going to do some multiplying. So this is applying, I'm going to kind of put a star up here, number 1. So we can actually calculate this by putting -5 out front and just multiplying that by whatever the normal integral from 3 to 6 is of f of x dx, right? So that would be -5 times the given information is -1. So the answer to part D is 5. So pretty straightforward thinking there, I think, for this group. Scroll way down here to get to the next property, and this is the last property for today. It's the additive interval property. It's kind of like the transitive property here. The thing that's switching around, you'll notice here, if we integrate the first one here in the orange, if we integrate from A to B and we find a point C in between, then that total area from A to B is equal to adding up A to C plus C to B. Okay. So just to kind of give a visual for this, this is just saying, like, if A is here and B is here and C is here, and we know that this maybe looks like 4 and this looks like 2 area-wise, that the actual integral from A to C, dx is going to be 2. That you can just combine those because B is within the interval A to C. So that's going to come up here in example 5. So we've got some line segments, and we have a kind of a composition of a bunch of line segments in a semicircle, and we've got 6 integrals down below that we are supposed to figure out. So I just want to make sure we draw a visual that goes along with each one of these, and then figure out the areas. So let's start with part A, just the integral from, again, we're looking at 0 to 2 for the f of x function. So 0 to 2, I just want to cordon off, right, along those x values, 0 and 2, that's the portion of this curve that I am finding the area of. So we know that's a quarter circle actually this time, so the area for part A is 1/4 pi r squared, right, and that would be a radius of 2 again. And so now we just get pi for that, but pi is not our answer for part A. Our answer is negative pi because it's situated below the x-axis, that area. Okay, B integrates from 2 to 6. So I want to shade that in with you, make sure we're talking about the same space. So 2 to 6 is this green triangle. I'll let you do that one on your own. C is from -4 to 2. So that's a combination of the theorem or property that's up here. So -4 all the way to 2 gives me all of this space here. Right? So I'm going to take that semicircle that I calculated for part C. I'm going to need the area of that triangle, right? 1/2 base times height. So actually let's use 2 for our base and 1 for our height. So the area of the blue triangle is 1. And then I've got, let's see, how can I write on this? So let's say the area of the blue triangle is, well, again, we're battling 2 ideas in our head. The area here is 1, but it counts as a -1 in terms of integration. And then we know, like before, 0 to 2 was pi, or negative pi, so I'm going to have another negative pi in my other half of my semicircle. So the total for part C would be a -1 plus a negative pi plus a negative pi. So that's -2 pi minus 1. Okay. Part D is from -4 to 6, so that is combining what you did in parts B and C. So add those two together. Part C includes throwing some absolute value marks. So that means that all of the calculations that we made below the x-axis are now going to be flipped up on top of the x-axis. So we're going to have 1 plus 2 pi, and then again your answer to part B should have been what? 1/2 4 units times 2 units. So that was 4. So our total for part C, when everything is absolute valued, or sorry, part E, would be 1 plus 2 pi plus 4. We expect a totally positive result for something that has those absolute values in it, like part C. Okay, and then F is a mind bender there. That's a really good question, asking us to find the value of f of x plus 2. So we have to combine our wits about us to do letter F. So this is a combination of a couple things. So first thing we want to do is we want to go up here to number 2, this particular property in this box, because that says that we can take things that we're supposed to add together in the integrand and we can split them up. So we're going to go back down here and let's split this up into 2 ideas for letter F. We're going to do -4 to 6 of f of x, that's the first part of that integrand, and then we're going to do -4 to 6 of the number 2. So -4 to 6 is a calculation, I think, that we had done in part D. which I didn't write down anywhere. That's the whole thing, right? So let's see. That's -1 minus 2 pi, and then plus 4 for the triangle in part B. So that total is 3 minus 2 pi, right? The net area. Negatives count for negative, and positive counts positive. The second one we have to kind of be a little bit savvy with. We're going to have to calculate this using the area, right? So we're going to have to sketch -4 to 6 are my limits on my x-axis. And then we got to think about what the function y equals 2 looks like, right? So I'll make that purple. So that's just a constant function, right? That looks like this. So if we kind of try to figure out the value of that integral, we have this big fat rectangle, right? That's got 10 units for our base and 2 units for our height. So the area of that part of this integral is 20 units. So my overall answer for f is to do 20 plus 3 minus 2 pi, our answer for the first half of the integral, which is 23 minus 2 pi. So that's what we get for part F. And then the last thing here is example 6, just a little AP style question. I'm going to see if you can think your way through this one, and have you try this one on your own, and then see if you get it right. And then we'll probably lead off with this one at the start of next class.